Our plan today is we're going to do a whole bunch of example on just analytical limits, show you a bunch of different situations and the tricks we can use, and then try to consolidate that together into like a flow chart. Tell you like, if this happens, and it looks like this, then try this, so we can kind of build something out, okay? Just as a heads up, Monday, I won't be here. I have jury duty potentially. So we'll see if I actually have to go in for or not, but it's Wayne County and they have like a million trials every day, so like I'm pretty sure I'll be there. So I'll probably leave you an assignment on this topic to work on while I'm gone, either via Delta Math or out of the textbook. I haven't sat down and figured it out yet, but it's on my to-do list. Okay. Just as a heads up, though. So we're gonna bypass any classwork time today because I know I'm gonna like burn a whole class period on Monday. So I just want to get through this stuff to where you have a chance to be able to like we've done enough practice in here to where you can see stuff on your own on Monday.
Yes.
Okay. So we're just kind of continuing on talking about these. It's a great day, isn't it?
Yeah, that's really how I feel like all day.
I'm hoping this is a one-note issue.
Me too. Like disconnecting. Like it. I couldn't click on Spotify, so I had to do it on my phone. And then I know my link over here from you.
There we
I
go.
want to know if that's right or not. So
Give me the
it
one.
when I said something, it wasn't working. Hear me. And then every time the map, it's like.
All right. So to this point, we've been focusing on limits where x approaches a finite value, right? We're going to continue talking about a few more situations, and then we're going to transition into what if x approaches an infinite value, where direct substitution is no longer really kind of viable, and look at kind of what we can do there. Everybody's good to start?
Yeah.
Okay. So we're doing just like situation where x approaches a, where a is finite, right? It's like an actual number, not an infinity. So we've looked at we started with a rational function. Say we have something like this. The limit as x approaches 1 of x squared plus 1 over x squared minus 2. First step on any analytical limit is going to be try a direct substitution, right? If I do that direct substitution, I have like 1 squared plus 1 over 1 squared minus 4. That's our answer. Done. Right? The direct substitution just spits out a finite value. Don't think twice about it. Just you're done. Celebrate. It's as easy as it can get, right? Okay. Now we also saw that. Bless you.
Bless you.
Sound like wet ones.
He's lying, guys.
So we also saw, we can try a direct substitution and we get indeterminate, right? Okay. What was our solution? What was the first thing we should try if we have a rational function? And go, yeah.
Factor the top and bottom.
Let's try to factor and reduce, right? Factor that guy up. Maybe something nice will happen. So hopefully that you guys see how to factor this. It should be pretty easy. This is like, like algebra 1, 2 factoring, where you have like the coefficient is 1. It's like as easy as it gets for a quadratic, right? Yeah. And what do we notice? Yeah, the x squared or the x plus 2's can cancel out of there, which is great because that's the part that's giving us the 0, right? If x is going to -2, that was the part we had to get out of there. Fantastic. So then we write again. And if we try direct substitution now, oh, that's a 4. Come on, dum-dum. Feel good? These should be like your bread and butter kind of limits. These ones like this is pretty straightforward, should feel very natural, very much like the stuff you did in algebra 2 and pre-calculus when you dealt with rational functions. Just have this limit thing in front of it. Big whoop, right? We're just factoring and reducing primarily, and that's should feel pretty comfortable. Yes? Okay. All right. Enough of these, right? We should feel okay there. That usually feels pretty familiar. The next situation is that we looked at was where we had like a radical going on there, right? So let's say we have let's do something like this. So again, we want to start the same way, right? We want to start with that direct substitution. If I do that, I'm going to have, bless you. I get that indeterminate form, right?
Yeah.
Okay. What was the trick here if I have like a rational thing, or a radical? Yeah, let's multiply by the conjugate. Whenever I see radical plus something, conjugate's going to be a pretty good idea. So what would the conjugate be of this? Good. Square root stuff plus 3. Do that to the top and bottom. And then what was my tip for the easy way of thinking about multiplying this out? Yeah, we want to think about this as like a difference of 2 squares, right? Like I have an a minus b here and like an a plus b there. Everybody's okay? Remember this? So when I do that, I'm going to get a x squared plus 9 minus 9 over, and then I'm never going to multiply out the pieces that aren't or difference of two squares, I always just I'm gonna leave those in the factored form because at some point I know I'm gonna need to do some kind of reducing. Everybody's okay with that notion? Okay. Notice in the numerator I have a plus 9 and minus 9. Whoop. And that's going to leave just an x squared in the numerator, right? And I have a factor of x squared in the denominator. So I can reduce that out of there too, leaving just the 1 in the numerator. Is everybody okay with the work I've shown? I've condensed a couple of things into one line there. Do you follow what happened?
Yeah.
Okay, you're okay with me condensing and not trying not to take like 3 lines on your paper to do this? And at this point, if we do our direct substitution, I end up with 1/6. I think this was the exact same problem we did last time, wasn't it?
Yeah.
Not creative enough. Sorry, guys. Is everybody okay? Now, let's do another one kind of like this. That's could work a little bit differently depending on how you see things. Hold on. Yeah. What's going to happen if we do a direct substitution?
0 over 0.
0 over 0. Can I start just doing this and not filling things in? I think we're comfortable enough with like what am I doing now that I can start condensing a little bit of the work and not writing quite as much out. Okay. What do you think here? What should we do?
Multiply like the denominator on both the bottom and top.
But the conjugate of the denominator.
Yeah,
right?
yes.
Yes, we can do that. And this is okay to do. This is going to work. I'm going to show you in a second, though, that there's another way of thinking about this particular problem that might have been even easier. Okay, so we can do that. I'm going to scroll this up a bit. Now, I have that difference of two squares thing going on in the bottom, right?
Yeah.
Can I just write out the thing? Right, just going to be x minus 1. Can you guys see that? Without me labeling all the difference of two squares stuff. Okay, if not, stop me and ask, and I'll fill in some more details. I just want to sometimes I'm just going to say it and write what I did and write the result rather than writing out all the steps just to condense a little bit.
Can you show me that one?
Well, just right? So I have square root x squared. Is that okay? We're good, right? And then on top, again, there's not a difference of two squares there, so I'm not going to monkey around with that at all. What do you notice, though? Yeah. And now if I do my direct substitution, I'm just going to have just
Wait, isn't you're going to 1 or 0?
well, I plugged 0 in, right?
Yeah, but on the first one you have 1.
Oh! Ha! That's just yep. Good. Good. Yes. Yeah, that's just me making the most, like, Mr. Kulik mistake possible. There we go. It's like I do the problem, I do all the hard parts right, and I copy the thing down wrong. Like, it's lovely. Those are the hardest mistakes to find, right? It's like all the algebra looks good. Well, you copied it down wrong. Okay. So this is good. This works, right? Can I point out that there's another way of thinking about this? I'm just going to drop some of this off, right? We started with this thing. When I see this, what I think is on top, that looks like a difference of 2 squares to me. Right? If I think about x as the square root of x squared, and then minus 1, I could do this in this fashion. It's the same you get the same result, right? Just a little bit different of an algebraic step there to get there. Is one better than the other? Not really. No, it's just kind of like what do you see when you look. But either approach is going to be okay. Could I have done that on the previous problem? No, because there's like not even a chance this was a factor of a difference of 2 squares kind of going on. But I just want to point that out there that, again, if you looked up like on an AI how to do this, they might have done something like this. And I want to point out to, it's like, yeah, that's okay. That works still. Yes?
I don't know how to do the difference of 2 squares.
So what we're saying is that, like, that's the difference of 2 squares, right?
Oh, yeah.
Right, so like, you can do this to factor, right? Or you can go the other way, and you can do this to avoid foiling.
Okay.
Right? So that's what we're doing, is depending on which way we're going, whether we can use it as a FOIL shortcut or a factoring shortcut. That's the idea.
Okay.
Is that
makes sense.
that fills in what you're missing?
Yeah.
Perfect. Okay. So far so good though?
Yeah.
Okay. Let's look at a new situation. Okay, so this will be like the third situation we've looked at. Let's do this one next, I guess. So let's say we have a piecewise function going on here. Oh, let's write it this way. Okay with the notation for the piecewise function? Clear as to what this means? As a brief aside, what's this going to look like? Can anybody visualize this in your head? Good. Yeah, so it's going to be half of a parabola and then like a line with positive sign. Right? Everybody can see that? Right? Parabola line. Okay. So to do this, if I want to find the limit of this, first thing I want to do is check to see where is this x approaching. And it's approaching at the boundary between the two pieces. Right? If it's not approaching the boundary, just plug into the appropriate piece. right? Like, let's do this first. So it just x approaches 1. Where does 1 live? Which piece? The quadratic or the linear? The linear piece, right? We're done. Just did a direct substitution. Right? Everybody's okay? We're going into the negative 1. What piece does the negative, where does negative 1 live? Quadratic or linear?
Quadratic.
Quadratic. So just plug in, right? Done. Okay?
Yeah.
What we can't do is if it's at the boundary. Oops. Okay. So, at the boundary, I'm going to need to use the definition of a limit. When is a limit? When does a limit exist? Good. When the left-hand limit equals the right-hand limit. So what I want to do is I want to check the left-hand limit and the right-hand limit. So I need to check both of these. Which piece of my piecewise function am I going to use for the left-hand limit? The quadratic or the linear? The quadratic, because that's when x is less than 0. Oops. And this is from 0, values that are less than 0, right? So I can do a direct substitution. Into the quadratic piece. The right-hand limit is going to be talking about the linear piece. So again, I can do a direct substitution into the linear piece. What do you notice? They are the same. So the overall limit is just 1. LHL stands for
Left-hand limit.
RHL is
Right.
okay. I don't think I've used that abbreviation before, but I thought it would be obvious, and I just want to make sure. Right? Good. You guys all were clever enough to figure that out. Does that feel okay?
Yeah.
So piecewise, unless it's at the boundary, it's just a direct substitution. If it's at the boundary, then you have to compare the left-hand limit with the right-hand limit, but those will still be direct substitution problems. Everybody's okay with that? That should be relatively easy to get. Does that feel good? Now, it's scary to look at. It's like, oh no, piecewise. But like, in terms of what you're actually doing, you're just plugging in like that. It's not too bad. Okay. All right. Okay. That should be sufficient, right? In terms of example. It's okay.
Question.
Yes.
What happens if they don't?
Then the limit doesn't exist.
Okay.
Yep. So like, if this was 2, right? Or this guy would be 2, then we'd say not equals d. So that was a what if question. I'm going to back off those marks though, so that if you go back and look at this, it's not like what the heck did Mr. Kulik do here? Now, I'm going to call this a difference quotient. Do you guys talk about difference quotients in pre-calc still? Okay.
What is it? Yeah.
All right. Yeah. So when I was you know, like when I was a wee lad doing this, we would have talked about difference quotients. Oh, I don't want that squared. I want that just x. Sorry. Talk about difference quotients. When we say difference quotient, basically we mean like something that looks like that.
I feel like we did. Yeah. And he was like, "Yeah, you'll use this in calc."
Yeah. That's what that technical term is. And what is that really? Difference quotient. Yeah, they're just slope, right? y2 minus y1 minus x2 minus x1, right? Very good. Right on. That's essentially, that's all that is. Where x1 is x, and, you know, x2 is a. Everybody's okay? Okay. So let's look at this guy. Again, if I try to direct substitute this, right, I get 0 over 0 again. So that tells me nothing other than, like, you need to algebra this thing through to find out what to do with this. Anybody with an idea? Yeah, really there's only one idea here. Let's like expand this out, right? Reminder, what does x plus 3 squared mean? Right? Means that you have to FOIL. It doesn't mean x squared plus 9. Right, just as a reminder. We call that the freshman's formula, because that's the kind of mistake freshmen make in math class. So let's not do that. So I went ahead and FOILed that out. Is everybody okay with me just FOILing in my head, not showing like the first order and last name? Okay. What do you notice in there? Yeah, and then I can take like a, you know, like a factor of x out, and then reduce that. Good. And then when we direct substitute, we just get 6. Right, 0 plus 6. Is everybody okay there? Yeah. So if we run into a difference quotient, almost always you just want to like expand that thing out. Easy enough to handle once you've seen the trick. Right? So all we're doing is like building out a toolbox of strategies. Like if my limit looks like this, then I do this. If it looks like that, I do this other thing. Right? We're just building out a set of tools for common problems that we run into. Let's see, was there any? No. Nope. Okay. So, this all look okay? All right. What happens though if we have like if my limit's going to positive or negative? I like to start here because here's the lovely part. You're gonna like this. You already know how to do this. problem without doing any algebra. With just the tools that Mr. Myers taught you, or Mr. Hulick in the case of James, taught you last year. So here is the key. Here's the key. If you're talking about a limit that x approaches positive or negative infinity, you're talking about horizontal asymptote behavior. Right? This is a rational function. What was the rule that Mr. Myers gave you guys for?
Bobotny needs DC.
Yes, that's the thing.
Oh, it's all coming back to me.
So
Wait, I got it. Bigger on bottom. 0.
So this is, what is the degree of the numerator?
2.
The degree of the denominator?
2.
2. So they're the same, right?
It's DC.
Which is the leading coefficient over leading coefficient, right? So this limit should just be 1. So sounds like there's some discussion. Tell me the letters here. It's Bo.
Botany.
So yeah, this is bigger on bottom,
0.
and then the limit would be 0 if the bigger degree is on bottom. Okay.
Yeah, DC.
Oh, thank you. Okay.
Bigger
on top.
Non-existent. And that's the slant.
So that's going to be either plus or minus infinity for us. It doesn't exist. Will depend on whether the leading coefficient is positive or negative, or we're talking about infinity going to positive or negative. We'll talk about that in an example quickly, but it means that it's going to behave like a slant asymptote. So like if you have a line like this going to positive infinity, it just goes to positive infinity, right? Or if it's going to negative infinity, it's going to negative infinity. If it's going down, like it's the opposite line, then it's kind of the opposite, right? So it's usually pretty easy. You just have to look at the difference of the degrees, whether it's odd or even, and then so it's not bad. All right, and then
These are the same. Exponents are the same. Divide coefficients.
right. Okay. So this is, if you have a rational function, you're doing an infinite limit on it, you already know. It's just the Bobotny stuff. I don't need you to show me any work. You can do it in your head. So this is,
So if you look at X,
just let me, okay? So to decide what to do, we just need to compare the degree of the numerator with the degree of the denominator, right? If the bigger exponent is on top, that's this guy, bigger on top. If the bigger exponent is on bottom, that's this guy, bigger on bottom. If they're equal, that's this guy, okay? So bigger on bottom, bigger on top, equal. If the bigger exponent is on bottom, then it just equals 0.
So then how did you get 1?
Because these are equal.
That's what I would do.
Yes, good. So this is the equal. So it's the degree, or divide coefficients. That's what it stands for. So I look at the leading coefficient on the top
Oh.
with the leading coefficient on the bottom.
Oh.
So 1 over 1. Does that feel better? Okay. And again, I know you guys learned the heck out of this last year. Well, okay. Well, in previous classes, this is something they connected immediately. It's like, oh, blah, blah, blah. I'm like, yes, whatever boo boo ba ba thing that he did. Like, if that's stuck, that's all we're doing.
Okay.
That's all that we're doing. Let's do another. Well, that's good because that's like a whole.
Godzilla poster.
An AI made it. And it was like an image of Bobotny eating DC.
Oh, that's amazing. That's amazing. Alright, let's do another, yes?
Oh, that's what.
What's this one?
Bobo. Zero.
Zero. Yeah, absolutely. Right? Do we have to do any algebra for this? No. All we have to do is look at the degrees, right? And we're done.
Is that every time it's going to?
Well, if it's a rational,
Oh, okay.
if we're looking at some other class of the function, what to do there in a moment. And I have to actually do a little bit of teach before I do get there, but yes,
So
go ahead.
on the last two where it says like x is going to negative infinity, like that doesn't really matter right now. Like
The only place where it would matter is in this case. And that's what we'll look at next, where their positive or negative infinity does mean a little bit.
Okay.
Okay. Everybody's all right? Is with it's the bigger on top one. So let's do an example of that. Bigger on top, right? So here I know this is going to equal positive or negative infinity. I need to decide which one. Here's how I decide. Both leading coefficients are positive, right? If I look at the degrees, the difference in the degree is even. In fact, it's 2, right? So it's basically, I'm looking at the end behavior for positive x squared. It's even, so both ends point up. So we're going to positive infinity. Right? So I'm just going to like default to my basic polynomial end behaviors where all I need is the sign of the coefficient and whether the degree is odd or even.
Sorry, I was still writing. Can you explain all the green again?
So this was going to equal positive or negative.
Right. We have to decide.
So to decide, I need to know what does that asymptote look like. So the two things I need to look at are the leading coefficients, whether they're positive or negative. Here I had 2 positives. And then the difference in the degrees. So the difference in the degrees is 2. And it has a positive leading coefficient. So this is going to look, the end behavior is going to look like x squared. As x squared goes to positive infinity, or as x goes to positive infinity for x squared, y goes to positive infinity. Does that make sense? Let's do another example, right? Yes.
So you just divide the two, like the x4.
Subtract.
Subtract them.
Subtract exponent. Well, the division of the
But like you divided like the thing.
yes, the leading coefficients. Yes, that's all I care about.
Okay.
I don't care about anything else that's happening.
Yeah.
Wait.
End behavior.
Wait, you divided to get the positive leading coefficient?
So all I looked at were these two.
Yeah.
If I divide those two things, I get positive x squared.
Yes.
That's the thing I want to look at as x goes to
If
positive.
there was coefficients, like it was like 3x before.
As I don't care. Is the end behavior of 3x squared
Oh,
different than x squared? No, right? All I care about is the sign, whether it's positive or negative.
I understand now.
Okay.
Do another.
Yes.
Try it out, right? Okay. And let's do this. Sneak some stuff in. First, what part of Bobobot needs TC is this?
Figure
Figure on top. Okay. So I care about the difference in the degrees, which is 3, But most importantly, I care that it's odd, right? And then I care about the leading coefficients. Negative divided by negative is positive. Right? So if I have a odd degree function with a positive leading coefficient, it looks like this, right? What happens is x goes to negative infinity. Yep. Done. So I'm just going to sketch myself a canonical picture. Like it doesn't have to be hard. It doesn't have to be accurate. And this is something that like you guys should be comfortable enough to do in your head, right?
Yeah.
I just want to reduce this problem down to what's the
For the leading coefficients, did you minus them or
division.
division?
Division.
Yeah.
Negative divided by negative
Yeah,
makes
it's
positive.
positive. Yeah.
Yes. Yep. Just like x to the fifth divided by x squared is x cubed. That's my odd degree, right? So it's just division. What do you guys think? This is the trickiest thing, but even this is like we can just reduce it down to something we're really familiar with by ignoring just ignoring everything but what's happening at the leading terms.
Yeah.
That's all I care about. Okay? What if it doesn't look like a ration?
And it looks like something else.
All right. So here, let's do this. F of x is an increasing function. And let's just say, we'll say k. Doesn't have to be a 1. Just some constant. What does increasing mean? So as the x coordinate gets bigger, the y coordinate gets bigger, right? Everybody agree?
Yeah.
Okay. So if I have a fixed number on top, but the number on bottom is growing infinitely large, what is this going to? So let's think about it, right? Yes. Right? So if you start like 1 over 1, 1 over 10, 1 over 100, 1 over 1,000, that's heading towards 0, right? We start with 1, 0.1, 0.01, 0.001, etc. We're heading to 0. Okay? Guys, this is wonderful. We can do this without doing any algebra. Just have to think for a moment. Okay? Let's think about the function sine x. What does its graph look like? Great. So its range is fixed between what two values?
2x, 0 to
Negative 1 and positive 1, right? Because the graph is stuck in between those, right? So we know this, right? So as x gets very, very big, the value of sine is still stuck between negative 1 and 1, right? Might as well just be a constant for our purposes. What's going to happen on bottom?
It's going to increase.
It's going to get super big, right?
Yeah.
So what is this heading to?
0.
0. So did the trig function matter at all to me? No, because I knew it was bounded between negative 1 and 1. It's going to act enough like a constant that I don't care. Pretty okay with that? Yes. Yeah, exactly right.
Is that only with sine?
Cosine would act the same way. The ones with the asymptotes, though, their range is all real numbers, so there you run into something indeterminate infinity over infinity, which we wouldn't address. That's a tool for another day.
Yeah.
But good question. Is everybody okay? All right. Let me think of another good one here to do.
Bless you. Wait, let me guess. We don't have to do any algebra.
Very minimal.
Oh,
Very, very minimal.
I forgot about E.
Where?
I forgot the E.
So
I have a day. He's my favorite letter.
that's good.
Oh, you know this?
I think it's all when it gets all.
Yeah, well, it's all.
God.
All right. So
Sure, on Christian
the trick here is I need that negative exponent. What is that negative exponent going to do?
Put one over it.
Yes. And now what's going to happen?
Oh, so that was the algebra.
That was all the algebra you needed.
Oh!
And now it goes to
0.
0. Because the bottom gets huge, top stays at 1. Because you essentially have like 1 over infinity, right? It's okay?
Yeah.
So in a way, these ones, your intuition becomes really valuable, right? So like, can you just kind of see what's going on? There's often not a lot of algebra to do. All right. So if you try to think about this like a direct substitution, what are we going to end up with? Infinity over infinity, right? So that's not terribly helpful to us. So what we need to think about instead is the rate of growth. Okay? Which one is growing faster, e to the x or x squared? E to the x. So compared, I'm sorry, to x, not x squared. Compared to e to the x, x might as well just be a constant. Because e to the x is growing so much faster than x is. Is everybody okay with this notion?
Yes.
So if I have e to the x over constant, what is this limit? Infinity. Okay?
Yes, because the growth rate is like significantly larger.
Yeah. So let's talk about growth rates of functions. So let's go slow to fast. Of the functions that, or of the operations of functions you guys have seen, what's going to be the slowest growing thing?
Linear.
Slower than linear.
exponential as it gets lower.
Oh, constant.
Constant, right? That has no growth at all, right? That's the slowest growing thing. Its growth is 0. Okay, good. Next up would be
Linear.
there's some stuff in between. I'm going to group it all together as polynomial. Right? Now, if you have 2 polynomials, how do you know which one's growing faster? The degree of the polynomial, right? Like like x squared grows faster than x to the first, x cubed faster than x squared, right? The degree will tell you all you need to know about the growth. Everybody's okay?
Yeah.
Okay. Now there's some stuff in here that still needs to be filled, but we'll save that. And we know that exponential is bigger than polynomial.
Yeah.
Right? We just saw that in the previous one, so that lives out there. What are some other things that we've run into? Logs, great. Where do logs live? Do they live in this gap or that gap? This gap, right? If I think about what the graph of like natural log of x looks like, it looks like this, right? That's for sure, less than y equals x. You guys agree? Okay. Okay. What else do we have that we haven't mentioned? Yeah. So sine, cosine might as well just be constants, right? Because they're locked between -1 and 1. That's good. What else lives down there? Well, tan inverse. Why does tan inverse live there? What's its graph looks like?
Sideways.
Like that, right? Where it has two horizontal asymptotes, it might as well be bounded between -π/2 or negative -π/2 and +π/2. Right?
Did you count it?
Flashback.
What's that?
Regular tangent? Because it's getting
So the problem with regular tangent, cotangent, cosecant, and secant, as you go to infinity, you have all those asymptotes happening, right? And sometimes it's growing very, very fast, and then grows very slow, because there's like a horizontal part where it's basically flat, and then grows really fast again and slow. So they're going to oscillate in a way that it's not going to be realistic to do. So those are kind of like indeterminate. If you see something like that in there, it's often just going to be indeterminate because it just oscillates back and forth, and I can't say anything about it, right? So Jack, as your aside, even if we asked you this, does this settle? Well, it's not a fraction, right? So who cares how it's growing? What's this function doing? What's the graph look like? Is it settling down to a value? No. So what are we going to say about its limit? Doesn't exist. And the reason we give here is we call this graph like an oscillating graph because it just keeps moving back and forth between values from -1 to positive, right? Okay. Let's think of other things that would live out here. So I would say this polynomial would even count for rational degrees. So like, something of the form like m/n. So like a x to the 3/2 grows faster than x to the 1st, right? So that covers radicals, fall all in there, and everybody's okay? Yeah. What else have you done that we haven't talked about? Is there anything else? Because there's other stuff I could put in here, but I don't know if it's worth putting in. It's still log.
All logs.
All logs. Yep.
What are the other ones?
Yeah, what are the other ones you're thinking?
Well,
What?
No.
factorials.
No.
Wait, like
talk
we did
about
table factorial.
Okay.
Yeah, we did. Okay, yeah, but did you
Just
find
that
it?
is-
That was like the thing after this. Was that like
How about x to the x?
Equation.
Is that one? I
That's on
I don't know what that is.
Yeah, it's not polynomial, it's not exponential, it's something different. That's the fastest growing thing you can get.
Work.
Oh, shoot. But if it's
Now, realistically, in this course, are you going to see those things?
Oh,
yes.
Exponential is the fastest growing thing you see.
That's good. I don't. I'm not too good.
Now, if you have two exponentials, how do you know which one's going faster? The base, right? Like 2 to the x is slower than 3 to the x,
Yeah.
right? That should be, nobody's surprised by that, I hope. If I wrote them down and asked you which one grows faster, I'm sure that everyone picked up the bigger base, right? But worth saying. Do you guys feel okay? Okay. All right, so let's go and use this now to do, say,
Oh my goodness. Oh my.
okay guys, it doesn't matter how many zeros are written down.
Oh.
I'll tell you right now, just like a bunch of zeros is fine. So I'm going to think about this the same way I would with Bogobot and TC, except instead of degrees, what I'm going to look at is growing functions. So where's the fastest growing function at, top or bottom?
Alright, Tom.
The exponential is the fastest growing. It's the fastest growing function is the exponential. This is bigger on top. So what's happening to the e to the x has a positive or negative coefficient? Positive. So as it goes to positive infinity, this is going to positive infinity. Didn't have to write anything down because essentially this is just positive leading coefficient e to the x.
Then why did we have to check if it's even or odd this time?
Because exponentials aren't even or odd. That's a polynomial description, right? Exponential functions all look like this, right? Or, I guess, this.
This is a really bad question, but
I guess or this.
negative infinity.
If it was negative infinity, this is a totally different problem.
Oh, okay.
Yeah, Jude, let's talk about that because that's doable. Okay.
I have a question.
Yes.
So
Sorry.
I thought because like that top like equation is like almost the same like equation as a rational like trinomial. So like what makes it different? Just because it has
E to the x. The variable's in the exponent. That's an exponential function.
Oh
I don't
right.
care about any of the other parts to it. As soon as I see that, I'm like,
Yeah.
The exponential is the only part of the top that matters.
Okay.
The bottom, polynomial. I don't care what the degree is because the exponential's on top.
Okay.
That wins.
Yeah.
That's bigger always. Doesn't matter if it has 10,000 zeros in the exponent. Right? If it's x to the 10,000 or 10 million or 10 to the 10 to the 50,000. Like the exponent, I don't care. It's still polynomial. So exponential still means.
Okay, thank you.
Is that okay?
Yes.
All right. Now you guys asked about what if this was a negative infinity here. Let's look at that real quick because that's a great question. And you guys feel good about what we're doing, right? We're just trying to build out some intuition, especially for these guys where it's not like, it's essentially everything turns into kind of like Bogobot in a way.
Yeah.
It's just like no longer talking about degrees, what we're talking about is the growth rate for the function. Okay, so we're just going to do this. How does that change things?
Well, it's in
So this is the way you want to think about it. Okay? Let me show you because this is not obvious what you want to do here to think about it more cleanly. Okay? So what I'm going to do is say, okay, this guy is going to be the same thing as, I'm going to take this negative on the infinity and push it into the variables. And then I'm going to make a positive infinity down here. And you'll see in a minute why I'm doing this. I don't know, some bunch of zeros. They count too many. Oh, yes, thank you.
Oh, it says equal, right? So how?
So I took the negative sign that we're going to negative infinity, and I pushed it into all the x's, and then turned it into a positive infinity. Okay? What is this doing? When x goes to positive infinity, what is that?
It's like,
Going down.
Right?
okay,
So it's going to
0.
0. So I don't care about it now. Now it's a standard Vogel-Botny problem. Bigger on bottom, so it goes to 0. Done. Is that okay? So recasting it with the positive infinity is usually the trick there. If it's going to negative infinity, you're like, ugh, what do I do with this? Just push the negative sign into all the variables and make it go to positive infinity and see if that makes life easier for you. That's often a nice habit if you're confused as to what to do. So that's a great question. We asked about the negative infinity. Good question, right? Like, that's a nice trick to have seen, right? Because that's coming up with that on your own. Would you come up with that on your own? No. You kind of need to be shown that to realize that, like, oh yeah, of course that's something I can do. Because, you know, like if I have just, obviously this is going to be the same thing as that, right? They're both going to give you negative infinity. Right, that's kind of what we just described. Yeah. Is I can take the negative from the infinity and push it onto the variable, and you should get the same thing if I go to positive infinity then. Yes, see it there? In the simplified example, it becomes really obvious that, oh, sure, that seems like that should work.
Yeah.
How am I doing on time? What do we got left?
11 minutes.
Okay. How are you guys feeling on what we've been doing today? What's that? 7 on 10.
Yeah, that's a good
7.5.
So,
I just need some practice. It's like
Yes.
a end of I don't know if I can do it
Okay.
alone.
Yeah.
So-
I need a lot of
let's write out a couple and
Okay.
just, you guys can work on them for a few minutes and then I'll go through and just kind of write the answers and maybe we have time to talk about them, maybe we don't, but at least it's like, you got to try and get a little bit of right-wrong feedback.
Okay.
Deal?
Yeah.
And that'll finish things out. Okay. So I don't know. We'll do like, I think we'll probably fit 4 on the board here. Do you guys want finite or infinite, or does it matter?
Let's-
Whatever you
Whatever
say.
you think we need to do.
One
We
each.
practice on
Let's
it.
see if we can do this.
Yeah, right. That would be okay.
There we go. That's the stuff right there. That's the stuff. Oh, sorry. We gotta get this all on the same screen. Last one. Sorry, guys. That should be plus. If you're like, I don't know what I don't see what difference that's gonna make, that's okay.
Yeah.
I don't
I
know.
lost that scene.
Let's do this. I'm gonna make one more change.
That check you made it negative infinity? Oh, man. I made it harder.
Because if you join substitute,
The last one? What about the
Yeah. And I'm gonna do this just to make it one. Do that. Put a little plus one.
How did the plus one change anything?
Oh, it makes a big difference.
Yeah, a one.
Yeah, that little plus one down there makes a
oh,
big
because
difference.
it is.
Huh. I don't really see it. I must be doing something wrong.
We finish at 40 or 45?
40.
Okay. So at like 37 or so, I'm gonna start writing some answers in, so you guys can sit and think for a minute, for a few more minutes. Yeah, that's excellent. If you got like half of them right. These are not easy problems, I know.
I think I got the first two right.
Oh, yeah, they're not
First two right.
Wait, I'm getting indeterminate.
Yeah, I didn't even me too on sleep.
Yes,
Then I don't know what to do.
Then I
just skipped it. Wait, I think I got it right. But then I don't know how to break that down. I just skipped it.
What's that? What's the names?
So what's the way I can do this without
Oh,
doing
because it's
this?
approaching infinity, so yeah. She's right.
I say because it's hard, and then it's
Yeah.
I don't know. Odd
One
positive.
plus one. Okay.
This is true.
That's why
No, you didn't do the Christian file.
What?
That's my fault.
Oh, I got 0.
Just fine.
Here, but
Can't do.
okay.
I got 0.
Okay.
No, wait, what?
Hold on. Let me explain why.
Whoa.
So I.
Oh, because the X.
what value can cosine
Oh, we can't
take
do
on that would be a problem? If the top is 0, can cosine be 0?
No.
Well, it can, right? Like that's one of the values in its range. But 0 over 0 is indeterminate. We can't eliminate the possibility of an indeterminate in there, so that's not actually one we can do. That was my bad. I should have figured that.
It's okay.
Yeah.
So, is C also the same?
No. No.
See,
I got 0 over 0.
Nope.
what? Okay, then. Me too, I got 0 over 0.
0 over 0. So I got 0 over 0.
How
Oh, I got 6.
does that?
Oh,
How
I
does
got
that
6
blow
too.
your mind?
Oh, it's close.
No, I promise, bro.
I have 6 down.
Wait, somebody explain.
I put 0 into everything and then I got 6.
Oh, I got right.
I got that
Oh,
one.
is it because
Yeah,
Oh, I got that right.
But I don't see how
Yes,
adding 1 changed that.
Each of these go to 0.
Yeah.
If I didn't have the plus 1 down there, I'd have 0 over 0.
Right, so I was actually pretty close.
So, I'll show you.
So I just wasn't paying attention.
So this one,
That one?
if I had written it instead like this, would that have given anybody a hint as to what to do?
Well, I mean, I got 1 plus 5 minus 6. So how's this?
Wait,
No, I have
I just did direct substitution.
Definitely would not.
Doesn't it look like a quadratic after I write this as like e to the x squared?
How's it not like this?
E to the 0 is 1.
Oh.
Oh.
That's what I
That's
thought.
why
I got to this point. I got to this
That's
point.
why I
I
pulled my
got 6.
calculator out.
That's excellent.
That's
No
why I
problem.
got 6. Yeah. That's what I got to this point. I got 6, but I didn't.
Wait,
need it, but I was just
I wait.
Right.
I didn't know.
I just left it in the form it was in. Why can't you just plug in 0 for where it is at the
Yeah,
end?
0 for 0.
Oh, that's what I meant. You're right.
You do
Okay.
20, Ed. Christian's very
Oh, wait, you're right.
Yeah, because I thought
So these are the only parts I care about.
Oh, so
The quotient of these is negative x. As negative x goes to positive infinity,
It's negative.
negative infinity, right?
It's odd.
Because it's pointing down. Because it's an odd degree with a negative leading coefficient.
Let him understand it. Let's just minus the degrees. And then it's odd.
that's a big one.
That's how it was.
So
I trusted you.
this was probably the one I got most of you guys on. Ha ha ha!
Yeah, you did.
The old, like, let's make an exponential into a quadratic factoring problem for you.
That got me for sure.
So Monday I'll have some delta math probably to practice some of this stuff, which I think is probably good because it'll give you the right or wrong and let you tell you how to do it after you make a mistake or whatever.
And then I know we have limits 1 and 2. Do we have any other homework?
No.
Because there's like analytical
Yes.
1, but don't do that.
That's probably going to be your Monday.
Okay, so don't do anything else if we finish limits
Right.
1 and 2.
Yeah, so your homework for Sunday is just the 2 delta math limits 1 and 2. That's it. Anything past that, we'll do it in class. We'll do it in class on Monday without me. Or maybe with me. Maybe I'll be here. I don't know. Maybe Wayne County will be like, yeah, we're not having these trials the week of Labor Day weekend or something. I don't know. Bye, guys. Have a good day.
Yeah.
I'm eating right now.
That's